Hi everyone. So in this video, we are going to take a look at how we can numerically approximate solutions to differential equations, even if we don't know a formula for the solutions. So let's consider the following model. P is the population of fish, let's say in thousands, present in a certain lake T years from today. And we've got the differential equation, which is given below. So dp dt is 0.3 p times 1 minus p over 10. And so let's just say initially the fish population at time 0 is 5. So there's 5,000 fish in the lake. How can we use this differential equation to calculate the rate at which the population of fish is going to be initially changing? So at these initial conditions, we have t is equal to 0 times 0, and the population p was equal to 5, so that was our 5,000 fish. So to calculate the rate of change, we would want to know what is dp dt at this initial condition. So everywhere I see a p, I'm going to plug in our initial population value, which was 5 for the 5,000 fish. And if this formula had a place for t anywhere, then I also would plug in the 0 for t, but it doesn't. And so simplifying this gives us 0.75, and this is a rate of change. So we have units, thousands of fish per year. So this is telling us at what rate is the fish population changing initially at time 0. And so next, let's see how we could use this information about the derivative at time 0 in order to make some approximations for the fish population, say 2 years from now, 10 years from now, or say 6 months out from now. Okay, so let's start with the first one, which is asking us to make a prediction for the fish population 2 years from now. So, we know that initially the fish population is increasing by 0.75 thousand fish per year. So after 1 year, it would go up by 0.75. After 2 years, if we want to calculate by how much has the fish population changed, what is delta P, we would take the rate of change of the fish population and then multiply by how many years out we want to extrapolate this by delta T. So for the first one, we would take the rate of 0.75 thousand fish per year, multiply it by 2 years to say that the fish population is going to increase by approximately 1.5 thousand fish over that 2-year span. So we started with 5,000 fish at time 0. If we're approximating that the increase was about 1.5 over that 2-year span, then after 2 years, the fish population would be approximately 6.5 thousand fish. Okay, so in 10 years out, we're going to take a similar approach. And that is, first, we can calculate by how much is the fish population going to change by approximately. So delta P is going to be approximately the 0.75 thousand fish per year, now taken over times 10-year span that we have. So that would give us a change in P that we're estimating to be 7.5 thousand fish. So if we started with 5,000 fish, go up by 7.5 thousand fish, that means after 10 years, we can approximately have about 12.5 thousand fish. Okay, and finally, for the last one, if we want to make a prediction for 6 months out, then our change in fish population, delta P, now would be approximately the rate of change 0.75, and now the change in time is half a year, so times 0.5. And that would give us a change in the fish population of approximately 0.375 thousand fish, and so that would be our increase. So we would add that to the original initial amount of fish, which was 5,000. So this approximation would be 5.375 thousand fish, and that would be our approximation for 6 months from now. And so a lot of these ideas should sound familiar from calculus, and that is we can use derivatives to approximate values in the future. And so if you might want to ask yourself which of these approximations that we made in B do you think would be most accurate to the actual value? So do you think it's best to extrapolate for a small amount of time or for a large amount of time or somewhere in the middle, or does it not make a difference? Okay, so is it a good assumption that the population is going to continue to grow at a constant rate, say that 0.75 thousand fish over a 10-year period? Well, the answer is, of course, that's not going to be the case. The differential equation tells us exactly that the rate of change, the PDT, is changing as the population changes. So after 6 months, the population has increased. That's going to affect the rate at which it's growing. And we can see that this is a bad approximation by using the slope field, for example. We can see that the slopes are changing by these arrows. So assuming that the slope over here is the same for all of these values of P, that's going to give us quite a bit of error in our approximation. Okay, so going out 10 years is a bad idea because we should be updating the rate of change. But if we extrapolate this out for 2 years, that's going to be not as much error. So let's think about improving on the estimate 10 years from now let's first go out for a smaller period of time, 2 years, and calculate what the fish population is going to be 2 years from now based on the rate of change that we know today. And that we already calculated was this 6.5 thousand fish. And so looking at the slope field down here, we can see that value over here is a little bit above 6. So that's where we get that estimate. And then at this point, we can go ahead and recalibrate the slope. And then using that slope, we can make a prediction for the next 2 years, and now we're 4 years out. And so to summarize what's going on here, what we're doing is after we get our estimate, say for 2 years, we use the new value, that 6.5 thousand, to recalibrate our slope. And then we made a prediction for the next 2 years. And then we can repeat this again. So we could approximate, okay, the value of Y, or the value of the fish population over here, something close to 8. Let's use 8 in the equation for the slope to then calculate the next approximation. And that we can see over here. And comparing this to what you can imagine the actual solutions would look like from the slope field, we're doing a better job than that initial estimate that we had that just said, let's just use the first slope and take that all the way out for 10 years. And so you can see if we took this all the way out to the extreme, we get a pretty good estimate. Just recycling this old idea from calculus, but just doing this in a step-by-step method. So when we look at the picture, we can think about this as like the tail to tip method of taking one arrow in the slope field and then attaching the next one and the next one and the next one. And so to conclude this video, some of the ideas we'll explore in class are how can we improve this approximation method even further, and how can we formalize this method? So it seems very algorithmic, so how can we come up with a recursive process for this method?